Okay, so in the last video, we saw the most basic of all results for statistical mechanics. We saw that if we can count microstates, if we can calculate or find somehow this quantity W of E and V and N, the number of microstates in the system as a function of energy, volume, and mole numbers, then we can get entropy, and then we can get all thermodynamic properties. It's also possible in principle to calculate all statistical properties, even for systems that are tiny and non-ergodic, as we'll see in a minute. So we really have everything in principle already. In just a couple of pages, just a few minutes, we already have all the basic principles, enough to derive all the rest of statistical mechanics. But of course, all that deriving isn't easy. And so the rest of what we're going to talk about are the implications of this basic result that we already have, which follows right away from the ergodic hypothesis. All right. We're going to improve things now in a couple of ways. First of all, we're going to start looking at an open system. The ergodic hypothesis only applies to isolated systems, but most of the systems we're interested in are systems that are open. It's not very often that you encounter in actual real life, in real practice, a closed or isolated system. So we're going to generalize things to deal with the more common case, the more interesting case. Second, it turns out to be very difficult, except in the very simplest of cases, to actually find out or calculate what this quantity W of E, V, and N actually is. And it also turns out, just by accident, there's no way you could know ahead of time, but if you go to an open system, a particular kind of open system at least, then it turns out the calculations are much easier. You go to a harder, more complicated system, and the calculations get easier. That's a nice thing. All right. So what are we going to do? We're going to consider a particular type of open system. There are many different kinds of open systems, but we're going to consider the simplest possible open system to begin with. And that's a system of some kind that's only open in one way. It still doesn't allow exchange of molecules, so the walls are still impermeable. Doesn't allow change of volume, so the walls are still isochoric or volume conserving. But the walls are not insulated, which means we can exchange heat with the surroundings, and so the energy is no longer fixed. Energy can exchange with the surroundings by heat exchanges. So no insulation, and we're going to assume from this point on, as we always have in the past in thermodynamics, that the surroundings act as a temperature bath as well. How can we do that? Well, the ergodic hypothesis only applies if we have an isolated system, but we can also, just like we did in thermodynamics, we can always consider the rest of the universe to be isolated. And then we consider our system, quote unquote, inside of that big, huge system to be composed of two subsystems, one of which is our actual system, the thing we're interested in, and everything else, the whole rest of the universe, is our surroundings. And because it's huge, or as big as we need it to be, it acts as a tea bath. That part is pretty easy. The rest, the next things we're going to do are apply all the ideas in a somewhat more complicated way that we just developed above. And let me say that the derivation I'm going to give here is different from all the textbooks. It's a simpler one, it's a more basic one, and it has the advantage that the traditional derivation, which is what Engel and Reed do, leaves you with a false impression that the Boltzmann distribution, which is what we're calculating next, this next result is the Boltzmann distribution. It leaves you with the impression that the Boltzmann distribution only applies if you have a huge number of copies of the system itself, and that just isn't true. All that's required for the Boltzmann distribution to apply and for the following derivation to be true is, first of all, the surroundings themselves have to be ergodic. So the ergodic hypothesis has to come in someplace But the system doesn't have to be ergodic. The system can be as small and simple as you like. It can behave in the absence of contact with the surroundings. It can behave in as simple a way as possible. But since it is in contact with the surroundings, the fact that the surroundings behave in an ergodic way, in a chaotic ergodic way, that's enough. The system itself can be simple. Second, we're going to require that the surroundings acts as a temperature bath. Of course, it will act as a temperature bath whether we want to or not, but we're going to require that it does. Third, we require that the system is only weakly coupled to the surroundings. That means that there aren't any springs attached to your system coming from the surroundings. There's no big interactions with the surroundings. The surroundings weakly perturbs the system only enough to allow transfer of heat between the two, but that's all. And the important thing about that weak coupling is that that's going to allow us to treat the system to be statistically independent of the surroundings. We'll see where that comes in as we're going through the derivation. And then finally, as I've been emphasizing up to now, the system can be of any size. It can be as small as we like. The system doesn't have to be complicated, and the system doesn't have to be ergodic. Even a single spin 1/2, on the nucleus of a hydrogen atom can be treated using the Boltzmann distribution, despite the fact that it's the simplest possible quantum system that there is. All right. Since the system is not isolated, the energy of the system isn't conserved, but the total energy for the total system, the system and surroundings, we're going to assume is conserved. So the total energy, ET, is a conserved quantity. That means it has to be a sum of the system energy plus the surroundings energy. And that means it will be useful to write the surroundings energy as the total energy minus the system energy. In other words, because the total energy doesn't change, when we're changing the system energy, we're also changing the surroundings energy, and that has big implications, as we'll see, because it affects the number of microstates available to the surroundings. We'll see how that works out. All right. According to the ergodic hypothesis, and that's what this is here. This is a version or a use of the ergodic hypothesis. The probability of finding our system with a certain system energy E is equal to the number of microstates, W, for which the energy of the system is E. So we're restricting the energy of the system. It's got to be E, whatever E happens to be, but we're not restricting anything else. That divided by the total number of microstates in both system and surroundings, no matter what E is. I put that in words, but it is just the ergodic hypothesis. I put it in words to make it hopefully a little clearer what quantities we need to calculate. All right. So the picture is this. We've got our system. It has energy E, and we're requiring that. There's a certain number of microstates associated with the system itself when it's got energy E, and we'll call that W of E. Out in the surroundings, though, there's also a certain number of microstates, and that number of microstates depends on the energy of the surroundings, and therefore it depends, because the total energy is fixed, it depends on the amount of energy in E. Whenever we pull some energy in from the surroundings, we're changing the energy of the surroundings and therefore changing the number of microstates available to the surroundings. Whenever we put some energy out to the surroundings from the system, we're also changing the energy of the surroundings and therefore changing the number of microstates available to the surroundings. All right, so with that picture, and assuming that the surroundings and the system are statistically independent, the number of microstates available to the system available to everything when the system has energy E is W of E, the number of microstates in the system itself, times W Sir, the number of microstates available to the surroundings. So when we change the value of E, we're changing both terms in that product. And that means that we can write our probability for finding the system in a certain energy E as, in the following way, the number of microstates available to the system times the number of microstates available to the surroundings divided by the total number of microstates no matter what, but that's just a sum of over all the possible energies of the system of the number of microstates available for each energy. So we have now we made a little bit more progress. We now have something a little bit better than just the words I wrote before. Can we go further and simplify it further? And the answer is yes, but we can't simplify this W of E much. We haven't said anything, we haven't put any restrictions at all on the system. We put some restrictions on the surroundings, but not on the system. And that means we really can't say much about this W of E. It can be any system, it can be any size, and therefore that W of E can be anything. It depends on what that system is. But the surroundings we have said some things about. We've said it's ergodic, and we've said it's a T-bath. So let's see what we can do with W Sir. First of all, we have that W Sir is equal to, where do I want to write this? The entropy of the surroundings is equal to KB times log of W Sir. That means that W Sir is equal to E to the entropy of the surroundings divided by KB. So if we can find an expression for the entropy of the surroundings, we can also find an expression for W for the surroundings. In fact, they're almost the same thing, right? I mean, they have the same information. This KB is just a fundamental constant, so we can, once we have S, we also have W. We have that the surroundings are a T-bath, which means that 1 over T is a constant, but that's also equal to the derivative of the entropy of the surroundings with respect to energy. And that means we can integrate this. This is basically a differential equation for entropy. And if we do, we get that the entropy of the surroundings is equal to some constant, some offset, plus the energy of the surroundings divided by T. A very simple expression. It applies only because we said that the surroundings act as a T-bath. If the surroundings were not a T-bath, then this simple expression wouldn't work. It also probably doesn't work if we get to too low of a temperature, but we'll see we can avoid that problem. All right. Now, it turns out that as the temperature gets close to 0, the energy of the surroundings also has to get close to 0. And that means, and it gets close to 0 in such a way that this term disappears. Well, if the temperature is equal to 0, then the entropy must also be equal to 0 by the third law. Entropy goes to 0 when T goes to 0. And now we see this term also goes to 0, so that means this S0 must be 0. And so we finally get that for the surroundings, for a T-bath, the entropy of the surroundings is just equal to the energy of the surroundings divided by T, and that means that it's equal to the total energy minus the system energy divided by T. All right, we now have that the entropy of the surroundings is equal to KB log W. And if we plug this, if we solve for W like I did earlier up above, we get that W Sir is E to the S Sir over KB. We now plug in our expression for SC, for S Sir, and that gives us this very important result. the number of microstates in the surroundings is equal to a constant, right? This is just a constant. This total energy is a constant. So a constant times e to the minus the system energy divided by kBt. What that is telling us is how the number of microstates in the surroundings depends on the energy of the system. The number of microstates in the surroundings is affected strongly, actually, by the energy of the system. When the system exchanges energy with the surroundings, it either causes the surroundings to gain microstates or causes them to lose microstates. When the system absorbs energy from the surroundings, reducing the energy of the surroundings, it lowers the number of microstates available to the surroundings. And when the system loses energy to the surroundings, raising the energy of the surroundings, then it causes the number of microstates in the surroundings to increase. All right. And that's what I'm saying here. You can read this in the notes on your own time. Let's see what I say here. The number of microstates available to SIR goes up rapidly when the system loses energy, and the number of microstates available to SIR goes down rapidly when the system gains energy. That's just what I said. All right. The rest now is just algebra. This is W SIR. And I've just plugged it into the expression I got earlier for the probability of finding energy E. And now this is just a constant up here. We can factor it out. It's also a constant inside this sum, right? It doesn't depend on the energy of the system, and so we can factor that out of the sum as well. Once you've factored it out on both top and bottom, it cancels on top and bottom, and that extra little factor just disappears, and we get our one version of the Boltzmann distribution, though not the most normal version, or not the most usual version. Remember that this is the probability for finding the system in a certain energy, but that could be a whole lot of microstates, right? A whole bunch of different microstates might still have the same energy. And this just tells you the probability of finding any one of all those microstates. Much more basic would be to find the probability of just one microstate. But remember, from the ergodic hypothesis, all microstates with the same energy have the same probability. That means that the probability of just one microstate is just the same thing that we found up here, but without this W of E here, right? That's telling us how many system microstates have energy E. Well, they all have the same probability. Therefore, just take away that W of E, and we get the probability of finding just one microstate. So here's the Boltzmann distribution as it's normally written. It says that the probability of finding one microstate, and I'm calling it microstate I, and what that I means may vary a lot from time to time, but it's a label for one microstate, whatever that happens to be, is equal to the exponential of E, the energy of that microstate, the energy of microstate I, divided by this quantity kBt, which is basically, we'll see in a minute, that's basically the available thermal energy. So the numerator in this probability is just an exponential in the ratio between the amount of energy that it takes to create microstate I and the available thermal energy. That has lots of implications. We'll talk about that later. Then in the denominator, there's a normalization factor. We'll talk about normalization factors a little bit later, but that quantity Q is a fairly simple quantity. It's a sum over all microstates of the system of the very same thing that's up in the numerator, only now summed over all the possible microstates. So if we can calculate these, if we know the energies of the system, we can, at least in principle, calculate this Q, and that gives us everything we need to know to calculate P. All right. There is one more comment I want to make before we do an example, and after the example I'll make a number of comments, because it's hard to overemphasize the importance of this result. It's a relatively simple result once you see how it works, and it applies just absolutely everywhere and explains much of thermodynamics. The last little comment I want to make is just that it is traditional to call the quantity 1 over kBt by the name beta. So that means that the Boltzmann distribution can be written in this following way. It's a little bit simpler. Instead of writing e to the minus e sub I over kt or kbt every time, we can just write e to the minus beta e sub I, and that's a little quicker. All right, we'll stop there and do this example, this relatively long but important example, in the next video.